So over to you, Niall, just summarizing additional elements of the recent PETRAS Phase 1 call on SDRIOTSS is the name of the project. This is a part 2, reviewing some of the outputs Colin previously summarized in part 1. Okay, thanks very much, Niall, for agreeing to give the presentation.
Yeah, no worries. So as Matt says, this presentation just sort of follows on from the presentation that Colin gave a few weeks ago. So I'll probably start out just giving a quick recap of some of the stuff that Colin went over, just for those of you who weren't at Colin's or have forgotten by now. And then we'll have a quick look at the kind of the hardware system overview of how we've moved this IoT spectrum survey algorithm onto the hardware that we're using. Have a quick look at kind of each processing stage involved in that. I've got a recorded video of the system running in sort of semi-real time, which I'll try and show, and then I'll have a quick look at some of the future work that's planned for this project. So this was a project that was funded by PETRAS, which is a cybersecurity hub made up of a consortium of universities and research centers. And they specialize in the cybersecurity of Internet of Things devices. Our project within PETRAS was this SDRIOTSS project. And our kind of problem space was what is out there. So as we all know, probably IoT devices are becoming increasingly common. There are more and more being deployed. And if you want to assess the security of the system, or you want to ensure the security of an IoT system, the first step in that is probably knowing what devices are in your environment. Are those devices your devices, or are there devices there that perhaps shouldn't be? And so our project was to take the Arista platform, which we've talked about before, it's a hardware platform that we have, and use it to sense what IoT devices are in this given environment. Now, I say IoT covers a whole range of different communications protocols, but based on the advice of our project partner for this project, which was DSTL, we focused on just the Lora protocol. And Colin went over this a couple of weeks ago, but the Lora protocol is quite a good protocol for us radar engineers because it uses a sequence of linear frequency modulated chirps. To start off with, there's a set of up chirps. Then crucially, there are 2 1/4 full down chirps. And then the message payload follows that, being encoded by the start frequency of the LFM. There's a lot of different kind of transmission parameters that are used for Lora. So the center frequency of these chirps, the bandwidth of the chirps, the spreading factor, which is effectively the chirp rate, and the coding rate. And this project looked not only to pick up Lora signals, but if you like, get the pulse descriptor word for these signals. So identifying what transmission parameters had been used for the transmission. Colin went through the software algorithm. The first step of the project was to develop a software algorithm to start picking these parameters out from recorded data. So Colin led on this part of the project and chose to use the Huff transform to extract most of the parameters. So the algorithm is kind of briefly summarized by these 4 plots on the left here. So to start with, the signal is spectrograms and thresholded. That's then thinned to give the chirps kind of a single pixel width. The thinned image is then Huff transformed to to pull out the linear features, so the lines. And then the results from the Huff transform are overlaid back onto the image again to identify just the down chirps in this. So the payload is difficult to pick out because of the changing start frequencies of the chirps, but the down chirps are a kind of a key fingerprint of LoRa signals. And so that was the detail that we chose to use to identify them. Having got the software algorithm working and tested that on a range of different LoRa signals, we were pretty happy with the performance of that. It was very effective at identifying and pulling out these parameters. So then we started to work towards deploying this on to hardware that might allow us to have a real-time system. And as I said before, the hardware system that we were using was the Arista platform, which is this Xilinx RFSoC system that we've been developing over the past few years. And the development work that's taken place on this has kind of been pushing towards having a multi-function RF sensor tool. And so within this project, we extended multifunction to include IoT spectrum survey, essentially. So as I said, the software algorithm was effective, but it required offline processing. And so we started to look at migrating the algorithm onto the Arista hardware. And the first step of that is to decide which algorithm steps will be executed by which hardware blocks which are available on the Arista platform. So the block diagram at the bottom here shows how we chose to partition those with the initial RF sampling and downmixing decimation done on the high-speed RF tile, which is part of the FPGA. Then a large part of the kind of hardcore number crunching was done in the FPGA fabric. So that included further decimation. It involved splitting the wide bandwidth sampled data into separate channels, spectrogramming those channels, thinning those spectrograms, rejecting noise, and then the final stages of the algorithm were done in the processing system. So that's in software effectively, although we used the Neon single instruction multiple data coprocessor, which is part of the system, to provide some hardware acceleration of those parts as well. So I'll just go through fairly briefly some of these algorithm steps and how we implemented them in the hardware. So first of all, the decimation, I think we've probably presented on that before, but that just used IP within the FPGA, which we had developed under previous projects. It's just a simple decimation filter. The channelization was a new problem, which we addressed during this project. And so channelization, essentially coming out of the decimator, we have an 8 megahertz bandwidth signal. And 8 megahertz of bandwidth, although it's not a lot, it's quite a lot if you want to start doing processing to pull out these narrow bandwidth LoRa signals. So the LoRa signals are between 125 and 250 kilohertz. So you don't really want to be looking across a whole 8 megahertz channel for them. So the idea was to split that 8 megahertz into 32 500 kilohertz channels, and each of the channels overlap with the neighboring channels by 50%. So any given LoRa signal will appear in its entirety in at least one channel, was the idea. And if you think about channelizing, then the perhaps slightly naive approach to doing this would be that you would bandpass. You would have a set of bandpass filters which selected the frequency range you wanted, and then you would downmix and decimate each of the outputs of those bandpass filters. But the disadvantage of doing that is that your filters have to run at the full data rate of your 8 megahertz signal coming in. So an alternative approach is what's called a polyphase channelizer. And this is quite a common approach to channelization because it allows your filters to run at the decimated rate. So instead of bandpass filtering and then downmixing and decimating, it allows you to decimate first, and then through some clever mathematical tricks, which I'll admit I don't fully understand, all of the images which are wrapped because they were above Nyquist for your decimated data are cancelled out, and you end up with channelized data coming out. So we spent quite a lot of time developing an implementation of this polyphase channelizer in the FPGA. And the kind of vague hardware design is shown in the bottom of this slide. So the first step is to serialize the data stream that's coming in from the ADCs. Then you reorder the data. You apply the filter. So sorry, the reordering is also doing the decimating. Then the filter stage. And then the FFT is the clever part, which cancels the images, and then repacking the data to send it off. Another key part of the hardware algorithm was to produce spectrograms. So we wanted a spectrogram of each of these 32 channels. Each spectrogram requires overlapping the data and zero padding of the data prior to the FFT. So whilst you're reducing your data rate for each channel when you channelize, when you start producing spectrograms, you're massively increasing your data rate again. From the software algorithm, we found that what we needed was a 64 sample window with a 58 sample overlap. So that's a 90% spectrogram window overlap. And then that gets zero padded up to 256. So this means that for every, for every 6 samples, you're producing 250 samples output from your spectrogram. And just to kind of demonstrate to you why it's worth doing this in hardware, this works out that for the full 8 megahertz bandwidth split into 32 channels, you're requiring something like 2.7 million FFTs per second, which requires you to be able to do those FFTs in about 0.37 microseconds. And on my laptop, which is a reasonable performance PC, requires 6 microseconds to do each FFT. So it's 16 times too slow for real-time operation just for producing the spectrograms. And so this was a big push then to try and get this implemented on the FPGA. The spectrogram block diagram, perhaps not particularly interesting. Again, we're having to deal with multiple channels here, so we split up the channels between different processing blocks so that they can be processed in parallel. Each processing block then looks something like this, with a block to do the data overlapping, block to do the zero padding, then FFT'd. We were actually implemented the windowing in the frequency domain, so it happens after the FFT. We've since realized that actually doesn't work very well, and so we're changing back to doing the windowing in the time domain. And then we're taking the absolute value of the FFT output. Some results from that. So here we see this was 2 LoRa signals of at different center frequencies that are transmitted at slightly different times from each other. And here I've plotted just the channelized output from 2 channels, which contain the complete signals. So you can see that the 2 different signals have been split by channel because their center frequencies are different, and then they're slightly separated in time as well. And if we zoom in on a section of the spectrogram, then you can see why the thinning process is needed prior to the Huff transform, because these chirps in the spectrogram have a finite width. It means that you could fit a straight line through them at all sorts of crazy angles that you don't want. So ideally, you want to reduce each of these chirps in the spectrogram to be just a single pixel wide, so that there's really only one line that you can fit through them. In the software algorithm, we were able to do that using a kind of image processing thinning algorithm, but that's an iterative algorithm that runs over the data many times and requires random access into the data. And so that's not very suitable for a hardware implementation. And so for our hardware implementation of the thinning, we actually did a bit of a cop-out, and we just took the maximum from each column in the spectrogram. That works very well, but it doesn't work if you're spectrogram contains more than one signal because it will only pull out one peak from that. The other issue is that if your spectrogram doesn't contain any signal at all, then you'll get just a random peak from the noise. So we realized that we needed a way to differentiate data where we had a valid LoRa signal and data where it was just noise. The way that we've done that, or several common approaches to that, would be just to do a sort of power level detection and throw out any data that was below a certain power threshold. People also use the KS statistical test to see whether the distribution looks like noise or whether it looks like a valid signal. But both of these methods are kind of sensitive to the absolute values of the signal that's coming in and the absolute values of the noise. And obviously this can change as you change perhaps the front end that you have on your system. If you added an amplifier or something, then suddenly your noise rejection algorithm wouldn't work very well anymore. And so the method that we've come up with is that we compare the normalized distribution of energy across the FFT bins of the spectrogram data. And we compare that distribution to the distribution of a sort of pre-computed noise reference. So in the plot in the bottom, I'm plotting here is the normalized distribution of energy across each column of the spectrogram. So in blue is the noise, or the expected output if it were just noise. In an ideal world, this would just be a straight line, but you can see that there's a steep section in the middle. And that steep section in the middle is due to some DC leakage through the channelizer. Then in orange and green, we see what happens if we have a signal and what happens if we have noise. So when we have a noise signal, it looks relatively similar to the noise reference. And we can see that we pull out the maximum difference between the two distributions, we get a number. And we could do that with the signal as well. If we define a threshold for that difference between what's signal and what's noise, then we can get quite an effective noise rejection algorithm. And this algorithm is relatively straightforward to implement in the FPGA hardware. The result of that is that every column in the spectrogram is now reduced to being just a single point or no points if it's noise. So the data plotted on this slide is the same as the spectrograms that I showed earlier, those two LoRa signals split into different channels. And now we've been able to reduce all of that data to just a few hundred points, which are the points within the chirps of the LoRa signal. And those points can then be passed to the Huff transform in order to extract the parameters. This kind of data reduction strategy is very important with these type of systems because running in real time, even at fairly small bandwidths, the amount of data that you're capturing is enormous. And as soon as you want to pass that over to software or you want to stream it off of the device, you very rapidly run into problems of being able to pass that much data. So being able to reduce this to just a few hundred points for each LoRa signal is very important. And that means that we can pass these points off to the processing system and we can implement the Huff transform and the signal parameterization in software. As I said before, this wasn't straight software. We also made use of this Neon coprocessor in order to parallelize the Huff transform calculation. Now, I'm going to show you, hopefully, let's see whether this works, show you a video of this running in real time, just to give you some idea of what this looks like. It's not the most exciting demonstration ever, but there you go. This is what you get when you can't all be in the lab and do show and tell in person. So what we've got here is the white terminal window on the left is the terminal for the Arista platform. And that is continuously running the hardware algorithm and the software algorithm that I've just covered. In the kind of black terminal window on the right, this is the control window for a Phi device, which is going to be our LoRa node for this experiment. And the Phi is configured so that I can type in different center frequencies for it to transmit at, and it will then transmit a LoRa signal containing some random data at that center frequency. And if I run the video, then what you should be able to see is that as different center frequencies are typed in and transmitted by the Phi, then the Arista platform detects those in real time and is able to extract what the center frequency was. This is actually a slightly old demo now. The most recent versions of this, not only is the center frequency extracted, but all of the other transmission parameters are extracted as well. So moving on to future work in this area, that's what we've sort of accomplished so far. But there's still quite a lot to do on this project. So the I talked a little bit about this DC leakage through the channelizer causing this kind of steepening in the distribution of energy and of the noise signal. This means that at the center of the LoRa chirp, it looks quite a lot like a noise signal to the noise discriminator. And so a lot of those samples get thrown away. And that can cause, if that region of no samples is too big, that can cause problems for the Huff transform. But we can rectify this problem by taking samples from the overlapping channels and joining them together in order to fill back in the holes which have been created by the noise rejection. So that should be a large improvement in the future, hopefully. There's quite a lot of tweaking and optimization work that needs to be done of both the hardware design and the software in order to get like a proper real-time system that's robust. And a part of that is that we need to further optimize how we're moving data from the FPGA to the processing system. We were recently awarded a phase 2 SDRIOTSS project, again funded by PETRAS, and that's going to start in January. And that project is going to focus on taking this initial system that we've put together and developing it into a full technology demonstrator system capable of real-time detection and classification of LoRa signals. So I think that is it for me. And Dylan or Matt, maybe if you could stop the recording then.